Okay, this problem tells us an engineer is going to redesign an ejection seat for an airplane. The seat was designed for pilots weighing between 130 and 191 pounds, and the new population of pilots is normally distributed with a mean of 139 and a standard deviation of 28.6. So the first question is, if a pilot is randomly selected, so we're just going to take one single pilot, find the probability his weight is between 130 and 191 pounds. So I find the z-score for 130 by doing 130 minus 139. It's always a score minus the mean divided by the standard deviation, which in this case is 28.6. And I get negative 0.31. And again, there's no reason to do this any more than 2 decimal places because the z-score table, Appendix A, can only go to 2 decimal places. Do the same thing for 191. So 191 minus the mean of 139 divided by the standard deviation of 28.6 gives you 1.82. Look both of those up in Appendix A, the z-score table, and you'll find that a z-score of negative 0.31 gives you 0.3783, which is this area right here to the left of, to the left of negative 0.31 under the bell-shaped curve. And if you read 1.82 off of the z-table, it gives you the area or the probability 0.9656, same thing. Then that tells you that is this area to the left of 1.82. So if I want the area in between these two, the negative 0.3 and the 1.82, then I need to subtract the 0.9656 and the 0.3783, and I'll get my answer of 0.5872. So that means that 0.5873 is between those two z-scores, the negative 0.31 and the 1.82, which represent the actual weights of 130 pounds and 191 pounds. So the probability that I pick a single pilot that his weight will be in this 130 to 191 range is 0.5873. If they had asked for it in a percent, it would be 58.73%. And it says round it to 4 decimal places, so I will leave it in those 4 decimal places. Then the B part of this problem asks us to look at a sample of 36 pilots. So now I know I'm going to use the central limit theorem because I'm talking about samples. And the only thing I do different when I work this problem is adjust the standard deviation. So when I'm working, because the sample size is 36, then I'm going to take the standard deviation they gave me, the 28.6, and divide it by the square root of 36. Now they gave me 3 digits, 286. So I put 3 digits here. But if you want to make sure that you don't have a rounding error, then you can put all of this in one step in your calculator, 130 minus 139 divided by either 4.77, or you can do like I did here on the second step and just put this in parentheses, 28.6 divided by 6. And then when you get that z-score, you need to round it to 2 places because that Appendix A table only has z-scores to 2 places in it. So we get our z-score for 130 and our z-score for 191 based on a sample size of 36. And the table tells you if you have a z-score anything over 3.5 to use 0.9999, so we did. And when we look up negative 1.89 in the table, we get 0.0294. We know that gives us the areas to the left of those z-scores, so if I want the area in between, then I need to subtract them. And so my answer to the B part would be 0.9705. And the C part asks you which would be more relevant. And since we're concerned for each individual pilot's safety, then the performance for a single pilot would be more important than the average.